A Zener diode is a diode which allows current to flow in the forward direction in the same manner as an ideal diode, but also permits it to flow in the reverse direction when the voltage is above a certain value known as the breakdown voltage, Zener voltage, Zener voltage, avalanche point, or peak inverse voltage. The device was named after Clarence Zener, who discovered this electrical property. Strictly speaking, a Zener diode is one in which the reverse breakdown is due to electron quantum tunneling under high electric field strength or the Zener effect. However, many diodes described as Zener diodes rely instead on avalanche breakdown as the mechanism. Both types are used with a Zener effect predominating under 5.6 V and avalanche breakdown above. Common applications include providing a reference voltage for voltage regulators, or to protect other semiconductor devices from momentary voltage pulses. Operation. A conventional solid-state diode allows significant current if it is reverse biased above its reverse breakdown voltage. When the reverse bias breakdown voltage is exceeded, a conventional diode is subject to high current due to avalanche breakdown. Unless this current is limited by circuitry, the diode may be permanently damaged due to overheating. A Zener diode exhibits almost the same properties, except the device is specially designed so as to have a reduced breakdown voltage, the so-called Zener voltage. By contrast with the conventional device, a reverse-biased Zener diode exhibits a controlled breakdown and allows the current to keep the voltage across the Zener diode close to the Zener breakdown voltage. For example, a diode with a Zener breakdown voltage of 3.2 V exhibits a voltage drop of very nearly 3.2 V across a wide range of reverse currents. The Zener diode is therefore ideal for applications such as the generation of a reference voltage, or as a voltage stabilizer for low-current applications. Another mechanism that produces a similar effect is the avalanche effect as in the avalanche diode. The two types of diode are in fact constructed the same way and both effects are present in diodes of this type. In silicon diodes up to about 5.6 volts, the Zener effect is the predominant effect and shows a marked negative temperature coefficient. Above 5.6 volts, the avalanche effect becomes predominant and exhibits a positive temperature coefficient. In a 5.6 V diode, the two effects occur together, and their temperature coefficients nearly cancel each other out, thus the 5.6 V diode is useful in temperature-critical applications. An alternative, which is used for voltage references that need to be highly stable over long periods of time, is to use a Zener diode with a temperature coefficient of plus 2 MV per degree Celsius connected in series with a forward-biased silicon diode manufactured on the same chip. The forward-biased diode has a temperature coefficient of 2 MV per degree Celsius, causing the TCs to cancel out. Modern manufacturing techniques have produced devices with voltages lower than 5.6 V with negligible temperature coefficients, but as higher voltage devices are encountered, the temperature coefficient rises dramatically. A 75 V diode has 10 times the coefficient of a 12 V diode. Zener and avalanche diodes, regardless of breakdown voltage, are usually marketed under the umbrella term of Zener diode. Waveform clipper. Two Zener diodes facing each other in series will act to clip both halves of an input signal. Waveform clippers can be used to not only reshape a signal, but also to prevent voltage spikes from affecting circuits that are connected to the power supply. Voltage shifter. A Zener diode can be applied to a circuit with a resistor to act as a voltage shifter. This circuit lowers the input voltage by a quantity that is equal to the Zener diode's breakdown voltage. Voltage regulator. A Zener diode can be applied to a circuit to regulate the voltage applied to a load. Construction. The Zener diode's operation depends on the heavy doping of its p-n junction. The depletion region formed in the diode is very thin and the electric field is consequently very high even for a small reverse bias voltage of about 5 V, allowing electrons to tunnel from the valence band of the p-type material to the conduction band of the n-type material. In the atomic scale, this tunneling corresponds to the transport of valence band electrons into the empty conduction band states. as a result of the reduced barrier between these bands and high electric fields that are induced due to the relatively high levels of dopings on both sides. The breakdown voltage can be controlled quite accurately in the doping process. While tolerances within 0.07% are available, the most widely used tolerances are 5% and 10%. Breakdown voltage for commonly available Zener diodes can vary widely from 1.2 volts to 200 volts. Surface Zeners, the emitter-base junction of a bipolar NPN transistor behaves as a Zener diode, with breakdown voltage at about 6.8 eV for common bipolar processes and about 10 eV for lightly doped base regions in BiCMOS processes. Older processes with poor control of doping characteristics have the variation of Zener voltage up to A plus or minus 1 eV. Newer processes using ion implantation can achieve no more than A plus or minus 0.25 eV. The NPN transistor structure can be employed as a surface Zener diode, with collector and emitter connected together as its cathode and base region as anode. In this approach, the base doping profile usually narrows towards the surface, creating a region with intensified electric field where the avalanche breakdown occurs. The hot carriers produced by acceleration in the intense field sometimes shoot into the oxide layer above the junction and become trapped there. The accumulation of the trapped charges can then cause Zener walkout, a corresponding change of the Zener voltage of the junction. The same effect can be achieved by radiation damage. The emitter-base Zener diodes can handle only smaller currents as the energy is dissipated in the base depletion region, which is very small. Higher amount of dissipated energy causes thermal damage to the junction and/or its contacts. Partial damage of the junction can shift its Zener voltage. Total destruction of the Zener junction by overheating it and causing migration of metallization across the junction can be used intentionally as a Zener zap antifuse. Subsurface Zeners, a subsurface Zener diode, also called buried Zener, is a device similar to the surface Zener, but with the avalanche region located deeper in the structure, typically several micrometers below the oxide. The hot carriers then lose energy by collisions with the semiconductor lattice before reaching the oxide layer and cannot be trapped there. The Zener walkout phenomenon therefore does not occur here, and the buried Zeners have voltage constant over their entire lifetime. Most buried Zeners have breakdown voltage of 5–7 volts. Several different junction structures are used. Uses. Zener diodes are widely used as voltage references and as shunt regulators to regulate the voltage across small circuits. When connected in parallel with a variable voltage source so that it is reverse biased, a Zener diode conducts when the voltage reaches the diode's reverse breakdown voltage. From that point on, the relatively low impedance of the diode keeps the voltage across the diode at that value. In this circuit, a typical voltage reference or regulator, an input voltage, UIN, is regulated down to a stable output voltage UOUT. The breakdown voltage of diode D is stable over a wide current range and holds UOUT relatively constant even though the input voltage may fluctuate over a fairly wide range. Because of the low impedance of the diode when operated like this, resistor R is used to limit current through the circuit. In the case of this simple reference, the current flowing in the diode is determined using Ohm's law and the known voltage drop across the resistor R. The value of R must satisfy two conditions. R must be small enough that the current through D keeps D in reverse breakdown. The value of this current is given in the data sheet for D. For example, the common BZX79C5V6 device, a 5.6 of V0.5 W Zener diode, has a recommended reverse current of 5 mA. If insufficient current exists through D, then UOUT is unregulated and less than the nominal breakdown voltage. When calculating R, allowance must be made for any current through the external load, not shown in this diagram, connected across UOUT. R must be large enough that the current through D does not destroy the device. If the current through D is ID, its breakdown voltage VB and its maximum power dissipation PMAX correlate as such. A load may be placed across the diode in this reference circuit, and as long as the Zener stays in reverse breakdown, the diode provides a stable voltage source to the load. Zener diodes in this configuration are often used as stable references for more advanced voltage regulator circuits. Shunt regulators are simple, but the requirements that the ballast resistor be small enough to avoid excessive voltage drop during worst-case operation tends to leave a lot of current flowing in the diode much of the time, making for a fairly wasteful regulator with high quiescent power dissipation, only suitable for smaller loads. These devices are also encountered, typically in series with a base emitter junction, in transistor stages where selective choice of a device centered around the avalanche or Zener point can be used to introduce compensating temperature coefficient balancing of the transistor pi/N junction. An example of this kind of use would be a DC error amplifier used in a regulated power supply circuit feedback loop system. Zener diodes are also used in surge protectors to limit transient voltage spikes. Another notable application of the Zener diode is the use of noise caused by its avalanche breakdown in a random number generator. Backward diode, transient voltage suppression diode, voltage regulator, references. Further reading, TVS Zener theory and design considerations. ON Semiconductor. 127 pages. 2005. HBD 854/D.